Hi, my name is Collins Weber, and I am doing the public lecture extra credit video for physics. In this video, I'm talking about my favorite lecture, which was the Chapter 10 lecture on types of collisions. Like most people going into this lecture, I knew that a collision is an interaction involving large forces acting for a short time, and this was my favorite lecture because we see collisions every day, and I found that this lecture was very practical to everyday life, and that's what I found most interesting about it. What I did not know going into this lecture that there are three types of collisions, and in all of them, momentum is conserved, assuming that there's no net force acting on the system. And these three types of collisions are elastic collisions, inelastic collisions, and maximally inelastic collisions. So in the video, I'll be talking about each one and giving an example. The first collision is an elastic collision, and in an elastic collision, the change in internal energy is equal to 0, and the final kinetic energy equals the initial kinetic energy. So in other words, the kinetic energy is conserved. In this small example here, there's a ball falling to the ground, and the ball starts out at T1 with kinetic energy equal to 2 joules. It hits the ground at T2, where it compresses at the moment of the collision, and at this moment the kinetic energy is going to equal to 0, so the potential energy will be equal to 2 joules, and at T3 the ball is heading back up, and at time T3 it's at the exact same location that it was at T1, and the kinetic energy at this point is equal to 2 joules. So all of the kinetic energy is conserved, and none of this energy was converted into thermal energy, which would be heat, or rotational kinetic energy. The ball's not rotating, the ball's not vibrating, so there's no vibrational kinetic energy, and the ball is not deformed in any way or shape. At this point, it's the exact same shape and size that it was at T1. So all of the kinetic energy at T1, which is the initial kinetic energy, is equal to the kinetic energy at T3, which is the final kinetic energy. However, this example is not exactly practical in everyday life, unless you had like an extremely super bouncy ball, and not even in that case would a ball fall to the ground and bounce back up to the exact same height. A collision is never totally elastic, but there are types of collisions that come very close, so this is why we study them. An example of a collision that's almost totally elastic would be pool balls or billiard balls. So I don't know how much a pool ball weighs, but I'm just going to say in this case that it's 2 kilograms, and that you strike the pool ball and it's moving with a speed of 10 meters per second, and it strikes a ball that is not moving at all. So once it hits this ball, it will no longer be moving, and the pool ball of the same mass that it collided with will be moving with 10 meters per second. And you can solve for this by doing the change of momentum equals 0, because in any collision, the final momentum will equal the initial momentum. So the second ball is not moving initially, and the first ball is not moving after the collision. So the mass of the first one, which is 2 kilograms, times the velocity, which is 10, is equal to the mass of the second one, which is 2, times its velocity, and you solve that after the collision, the second ball is moving with a speed of 10 meters per second. So that's how you solve for the velocity. Now, to prove that the kinetic energy is conserved, the initial kinetic energy is going to be equal to 1/2 the mass, 2 times the velocity squared, plus the mass, 1/2 the mass of the second ball times its velocity squared, which this is going to be equal to 0. So the initial kinetic energy will be equal to 100 joules, and the final kinetic energy is the same thing, because the first ball is no longer moving and the second ball is moving with a speed of 10 meters a second. So you get 100 joules. So this collision is elastic because the final kinetic energy is equal to the initial kinetic energy. Something not talked about in class that is, I guess, interesting, or something that anyone could learn, would be a time you would want an elastic collision, which would be in golfing. All golfers want their collision between their golf club and their golf ball to be as close to totally elastic as possible. They wouldn't want any of the energy to be converted into like heat or sound. They want all of the energy to be converted to kinetic energy because the ball will travel farther, and basically the velocity, you want the initial kinetic energy, which is the golf club. When it strikes the golf ball, you want the golf ball moving with maximum velocity because that's how you get it to travel further. So if kinetic energy is conserved, the golf ball will go farther. The second type of collision is an inelastic collision, which is when the change in energy is not equal to zero. The change in internal energy is not equal to zero, and the final kinetic energy does not equal the initial kinetic energy. So in other words, kinetic energy is not conserved, and there is some change, and this can either be the objects get hot, the object deforms, it could rotate or vibrate, and so on. There's many different things that could happen, but the main point is that kinetic energy is not conserved. An example of inelastic collision would be a car with kinetic energy of 60 joules colliding with a car of kinetic energy with 40 joules. So the total kinetic energy initially would be 100 joules. And after the collision, car 1 would have a kinetic energy of 35 joules, and car 2 a kinetic energy of 25 joules. So the final kinetic energy of the system is equal to 60 joules. So there's 40 joules of energy that is lost. And this energy is just converted into some other form. It's not kinetic energy. It's thermal energy or rotational or any other type of energy. An example where you would want an inelastic collision would be when you collide with the airbag in your car. You would want some of the energy to be converted into something other than kinetic energy. You want that energy to be absorbed and transferred into other types of energy. Otherwise, when you collide with the airbag, you would bounce back and shoot straight back out through your windshield. So the third and final type of collision is a type of inelastic collision. It's a maximally inelastic collision, and this is an inelastic collision in which the objects, when they collide, they stick together, and these objects will move together with the same velocity. So the momentum of the first one plus the momentum of the second one is going to be the total mass of the two plus the velocity of both of them because they're moving together with the same velocity. So the initial momentum will still equal the final momentum, and you can solve for the velocity of the two objects together using this equation. So I'll give you two examples. One example would just be a car crash. So if car 1, which weighs 26,000 kilograms, is moving at a speed of 55 meters per second, and car 2 is moving at 65 meters per second, and it weighs 1,300 kilograms. I don't know. This is 2,600, not 26,000. And they're each moving towards each other. Then when they collide, they will stick together and move with some velocity. We don't know in which direction or how fast until we solve for this equation. So the mass of the first car times its velocity plus the mass of car 2 times its velocity, and watch out for negatives. That's very important. Most questions you will get wrong in this type of problem will be because you forget the negative. So that's very important because it's moving in the opposite direction of this car. You could say that car 1 is negative and car 2 is positive, but just know that they're opposite. So you have to define your axis, and either way, in my problem, I'm just doing a standard XY axis. So this is the positive x direction, which means car 2 is traveling in the negative x, so it's traveling at negative 65 meters per second. And this will equal the total mass of the two, which is 3,900 kilograms, times the velocity of the two cars together. I already did some of the calculations, and it works out to be 143,000 plus negative 84,500, and this is going to be equal to 3,900 times the velocity of them together. And if you solve for Vt, you find out that Vt is going to equal exactly 15 meters per second. And this answer is positive, so that means the car will be moving to the right, or both the cars will be moving to the right. So if you look up here, both cars will be moving to the right at 15 meters per second. And that we found that out using this equation here. To prove that it is an inelastic collision and that kinetic energy is not conserved, we can solve for the initial and final kinetic energies now. The initial kinetic energy is going to be equal to half of the mass of the first car plus its velocity squared plus half the mass of the second car plus its velocity squared. And that's going to be equal to 6,678,750 joules. And the final kinetic energy is equal to 1/2 of the combined masses times their velocity, and that is equal to 438,750 joules. So as you can see, the final kinetic energy is not equal to the initial kinetic energy, which means it's an inelastic collision, and there's a loss in kinetic energy, and this loss can be to any type of, the kinetic energy is just going to be converted into another form of energy. Example 2 is going to be when the objects have equal and opposite momenta. So after they collide, they will be at rest. A short example of this is if ball 1 is 2 kilograms moving at 2 meters per second, and ball 2 is 1 kilogram moving at 4 meters per second. Then you can use this equation up here to solve for the final velocity of the combined objects. Don't forget the negative, and this is equal to the combined mass times the velocity of them together. So you get 4 minus 4 equals 3 times the velocity, and this works out so that the velocity of the two stuck together is going to be 0 meters per second. So they won't move after they collide because the momentas are equal and opposite. We can once again show that kinetic energy is not conserved by showing that the initial kinetic energy is equal to 1/2 the initial mass plus its velocity, or the first mass plus its velocity, plus 1/2 of the second ball's mass plus its velocity, and this works out to be 12 joules. And the final kinetic energy is equal to 1/2 of the combined masses times their velocity of them stuck together and moving, which is 0 because of the equal and opposite momentum that we proved up here. And so the final kinetic energy is 0.